Hey everybody, welcome back to another vector statics worked out problem video. In this example, we'll be dealing with a two-dimensional rigid body equilibrium problem. So there's a problem set up here. There's a inclined slope, and there's two brackets that are both hinged at point C and D, and they're attached to each other at point B. So this is a structures problem, which means it falls into the category of either a truss, a frame, or a machine. Now this particular problem is going to be classified as a frame problem because it contains at least one multi-force member, but it's not a machine problem because the way that the problem is constrained, there's no way that these brackets could actually move with respect to one another. But that doesn't mean that forces won't be distributed throughout different points on this frame. So we can see that there's a 150-pound force applied vertically at point A. And the question is asking us what is the force at point B, and that really means the force of the small bracket or the green bracket acting on the blue bracket to keep everything in equilibrium. So one way to think about this is you can imagine if the green bracket were not here and you just push down with 150 pounds of force at point A, well, the blue bracket would just, rotate or fall down and to the left. And it's only because the green bracket is there pulling it back in the other direction that everything remains in equilibrium. Okay, so as with most frame and machine problems, it's always a good idea to see if you can identify any two-force or three-force members first, because that could potentially give us some additional information that will allow us to solve the problem more easily. In our case here, if we look at the smaller bracket, the green bracket, going from point B to D, we can actually identify this as a two-force member, which means there's only two forces acting at points B and D, and those are the only forces acting on this bracket. And the property that we're going to leverage to give us some additional information here is the fact that all two-force members have two forces acting on them, and they share the same line of action. So what that means is the two forces here, there's a reaction at point D, and there's a reaction at point B. There's a line that connects those 2 points, and so the reaction at point D and the reaction at point B, those two forces share the same line of action. Now that has to be the case because if that were not the case, there would be some residual component in a direction that's not the line of action that would contribute to some acceleration. So we relied on this concept heavily when we talked about trusses. A truss is a structure that is comprised entirely of two-force members, and so being able to leverage the property of two-force members helped tremendously with trusses, and it's also going to help us with this problem. Now the way that I've drawn the forces here, I've drawn RD going down and to the right, RB going up and to the left. That's a little bit arbitrary. I made an assumption there, and as long as they share the same line of action, it doesn't matter if you draw them in the wrong direction, but they do need to have opposing directions. So I can either draw them both facing away or both facing toward the bracket. And nothing else about the mathematical process would change, except that when I get to the answer, if I solve for RB, if I get a negative value, that just means that I drew the arrows the wrong way to begin with. Okay, so the small bracket, again, two-force member. There's not a ton of information we can gain from this free body diagram, but there's one key piece of information that will help us when we do the free body diagram for the second bracket, the blue bracket. And that's going to be the direction of this force RB. So we were given some of the geometry here. We know that the top length of this bracket is 3 feet. The vertical length, or the side dimension here, is 1.5 feet. And what that will allow us to do is to solve for this angle here. We'll call that theta. And so theta is just going to be the arctangent of opposite, which is 1.5, over adjacent, which is 3. That turns out to be 26.6 degrees. So we can't really get the magnitudes of these forces at this point, but knowing the direction of this force is actually going to help us tremendously with the second part of this problem. So let's just box this up for now. We know the angle with respect to the horizontal here of RB. Let's see how that helps us with the second part of this problem. Okay, so this is the free body diagram for the larger bracket, bracket ABC. And what we can see here is in addition to the 150-pound force applied at point A, we also have a reaction at C. Again, because this is a hinge support, we're going to have a reaction in both X and Y directions. And then of course we're going to have R sub B, the reaction at point B. On this bracket, this force represents the force applied to the blue bracket by the green bracket as we push down at point A with 150 pounds of force. So at point B, this RB should be equal and opposite to that at point B of the small bracket. And the thing that we just solved, which is going to make this problem solvable for us, is the fact that we just figured out that angle theta. Now why that's important is because that's going to give us the direction of this force RB, which will allow us to break it down into its vector components and do our equations of equilibrium. Okay, so recall that the question asked us to find that force at B. So in other words, we're trying to find the force RB. And if you look at the free body diagram for the large bracket, there's one known force, 150 pounds, but there's three unknown forces, RB and the two reactions at point C. And because this is a planar problem, we know that we have three equations to work with. We have sum of forces x and y and sum of moments about any point should all equal 0. But because we're only tasked with finding this one unknown RB, we could be a little bit strategic with our math here if we take moments about point C. And the reason this is going to be helpful is because if we take moments about point C, then neither Cx nor Cy will impart a moment about point C because their lines of action pass through the point. So this is a more strategic way to apply the math here because in theory we'll just end up with one equation and one unknown, the reaction at point B, which is what we're looking for. Okay, so if we consider counterclockwise to be positive, which is a pretty typical convention, there's essentially two forces that are going to contribute to a moment about point C. That's the 150-pound force at point A and the reaction force at point B. Those are both forces whose lines of action do not intersect at point C, so they will impart a moment about point C. Let's just write down our dimensions here. We know that this dimension horizontally is 3 feet and this dimension vertically is also 3 feet. So the moment due to the 150-pound force will be, it'll have a moment arm of 3 feet. And because the 150-pound force is perpendicular to that moment arm, the moment is just the product of 3 times 150, and it's in the positive direction because this 150-pound force will tend to produce a moment about point C in the positive direction. Meaning, if you look at our convention for positive being counterclockwise, the 150-pound force would tend to rotate this bracket about point C in the counterclockwise direction, like so. So that's why it's a positive moment. Now there's a second force here, RB, that's also going to produce a moment about point C, and because this is a summation of moments about point C, we also need to add that moment as well. So because RB is not perpendicular to this vertical 3-foot distance here from B to C, the easiest way is to just revert to the definition of the moment, which is the cross product. Okay, so we're going to add to this moment the moment due to RB, which is going to be R from C to B. So it's the vector that's going from the point of rotation to the point of application of the force, RCB, cross the reaction force at B. And so all of that needs to sum to 0. And so we really just need to work out this cross product now to figure out the rest of this problem. So R from C to B, this is a vector that goes from point C to point B, which is actually very straightforward in this problem. If you look at the diagram, start at point C, the way to get to point B is to go 3 feet in the J direction. And that's it. That's the entire R sub CB vector. So that's how you get to point B from point C. RB, that's the reaction force that we're trying to solve for. We need to define this vector as well. And we don't exactly know the magnitude yet because that's what we're trying to find in this problem, but we do know the direction of the force. And that's really key here to solving this problem, is recognizing that we already figured out this theta, which means when we go to break down the RB vector into its vertical and horizontal components, we know that direction. So R sub B is going to have some component in the horizontal direction, and that's going to be equal to the magnitude RB, which we're trying to find, times the cosine of 26.6 degrees. And that's going to have units of feet, and this is a vector component in the I direction because it's going horizontally to the right in the positive x direction. And then there's also going to be a vertical component. That's this piece right here. And if you look at RB as a whole, it's going to the right, but it's also going downward. And that downward component is a negative piece that has magnitude RB sine of 26.6 degrees. And that has units of feet in the J direction. So even though we don't know what this RB value is yet, that's really the unknown that we're trying to figure out, we can still define the RB vector by using the direction that we figured out in the first part of the problem. And so bringing this equation down to here, 3 times 150, that's 450. It's going to have units of foot-pounds. And what we need to do is to add this cross product, RCB cross RB. The easiest way to do that, there's many ways to evaluate this cross product, but the easiest way is the way that we've been outlining in class, which is to just take the determinant of a specific 3 by 3 vector. So for this cross product, the top row of the 3 by 3 vector will just be all 3 unit vectors. The second row will be R, which in this case is just 0 feet in the I direction, 3 feet in the j direction, and then 0 feet in the k direction. And then the last row will be our vector rb, which has an I component of rb cosine 26.6, or about 0.89 rb, and it's got a j component of negative rb sine of 26.6, so about negative 0.45 rb, and it has no component in the k direction. And all of this needs to add up to 0. Okay, so if we evaluate this cross product, that just means take the determinant of this 3 by 3 matrix. If you look at the I component, if you isolate the I component, then we're just taking the determinant of this 2 by 2 matrix, which contains 2 zeros in the right-hand column, so that term is going to be 0. If you look at the j component, that would be j times minus the determinant of the 2 by 2 matrix comprised of these 2 columns. This is a very sparse matrix. There's 3 zeros in this matrix, so that determinant also becomes 0. So the only component that survives from this determinant is actually the k component, which even then only one of the 2 terms is non-zero. So the determinant of this 2 by 2 matrix would be 0 times minus 0.45 rb minus 3 times 0.89 rb. So the only component that survives here is going to be 0 minus 3 times 0.89, which is about 2.67, and that's going to be scaled up by rb. And just to be completely consistent here, that's actually a vector in the k direction. That's this piece here. And this 450 is actually also a vector in the k direction. And the reason we know that is because 450 was the result of this r cross this f. And so this r had a component in the minus x direction, and we were actually crossing it with a vector, this 150-pound force, in the minus j direction. And so the cross product of minus I and minus j becomes k itself. Okay, so just for clarity now, we've got 2 components that both share the same unit vector. So 450 foot-pounds in the k direction minus 2.67 rb foot-pounds in the k direction must add up to 0. And so because these are both in the k direction, we can actually equate those, and we can just come up with a scalar equation for 50 minus 2.67 rb. That's got to be equal to 0 when we sum the k components to 0. And so this allows us to solve for rb, the magnitude of that reaction force at point B, as 168 pounds. Right, so that's what the question was originally asking us for. What is the force acting at this point B, right here, of the small bracket acting upon the large? That's kind of a strange way to word the question, because that's the same force as the large bracket acting on the small. They're just in equal and opposite directions. So this question could have just said determine the force at point B. We defined that force to be R sub B, and we were able to calculate that force as 168 pounds. Now, for a little bit of bonus content, if you were asked to also find the reaction at point C, which is very common for these types of problems, well, doing that now would actually be really straightforward, because we've already figured out the reaction force at point B, and we used our sum of moments equation to achieve that. Well, again, since this is a planar problem, we only have 3 equations available for doing equilibrium in 2 dimensions. What we haven't used yet is sum of forces in the x direction must equal 0, and sum of forces in the y direction must equal 0. If you use those 2 equations, you can see pretty quickly that you'd be able to solve for Cx and Cy. Looking at the bracket here, I know it's getting a little bit messy, but if you look at the forces in the x direction, that's only the horizontal component of Rb in the positive direction and Cx drawn here in the negative direction. Those are the only 2 forces in the x direction. So if you took sum of forces in the x direction, set those equal to 0, what you would end up with is Rb, which we already know as 168 pounds, times cosine of 26.6 degrees, because that's the horizontal component of RB, minus Cx, and that would have to equal 0. So Cx just works out to be 0.89 of RB, and RB, as we know, is 168 pounds. So Cx is completely solvable at this point. If you look at the free body diagram again and some forces in the y direction, you'll notice that we have 150 pounds straight downward. We have the y component of RB also downward in the negative direction. And then the only thing preventing this whole bracket from accelerating downward would be the y component at reaction C, so C sub y. So sum of forces in the y direction equals 0. That just looks like Cy is in the positive direction, minus 150 minus RB sine of 26.6, which is the vertical component of our RB. All that has to equal 0. Again, RB, we know this is 168 pounds. So Cy is now solvable as well. It's just going to be 150 plus 0.45 of RB, which is 168. So Cy is completely solved as well. And so now we've actually found the reaction at point C as well as the reaction at point B. Okay, so there you have it, a rigid body equilibrium problem in 2 dimensions. This is a frame type structure problem, but it still follows the same process mathematically as most 2-dimensional equilibrium problems. In this particular problem, we leveraged the fact that one of the brackets was a 2-force member, and that was kind of the key observation in this problem because that allowed us to figure out the direction of that force RB. Now, some of you might have also sorted out that the larger bracket, the bracket ABC, that was actually a 3-force member. If you notice that at point A, there's a 150-pound force, at point B, there's RB, and at point C, there's a reaction force, which could be summed up as a single vector, which we could call RC. Now, because the large bracket is a 3-force member, we could have actually treated this problem without having to deal with moments or our equations of equilibrium. Anytime you've got a 3-force member, you can typically solve that using a basic force triangle like we did earlier in this semester. So there is an alternate solution to this problem which just uses the concept of the force triangle. And if you want to see that process, you can actually just check out the next video in this series where we do another rigid body equilibrium problem in 2 dimensions. But in that problem, we'll actually leverage the force triangle approach, which allows us to eliminate some of the more complicated cross-product math and so forth. So definitely check out that video if you're curious. And while you're at it, you may as well check out some of the other videos here that we have in the Department of Mechanical Engineering. We've got literally hundreds of videos produced by our own faculty in the department here for the specific classes in our curriculum. So again, if you're a student here, this is a really valuable resource. I highly encourage you to use this as a supplement to your courses that you're taking here. And if you're not a student here at Cal Poly Pomona, that's okay too. All our videos are free and open to the public, and so hopefully you'll be able to gain some knowledge as well. Okay, so that's going to do it for this video. If you have any questions, just drop them down below. We'll do our best to answer as many as we can. Thanks again for watching, and thanks for subscribing to our channel here at Cal Poly Pomona. We'll see you next time.